you know, deep learning, machine learning, artificial intelligence, those are all concepts that people in the public are deeply misunderstanding, okay? And it's not really surprising, especially if you consider the history of movies, okay? So we have, anybody know what this movie was? War Game, exactly, right? So in War Game, there was a computer which was almost causing harms to humans. There was a happy ending because it's a Hollywood movie, typical movie, right? So almost causing harm to human because it didn't quite understand what was expected from it, okay? It thought it was playing a game. Then you have, of course, 2001, Space Odyssey, right, where a computer killed people because it had some kind of moral conflict, all right? And then we have, of course, Terminator, no questions asked. He's just here to kill everybody. There is no conflict at all here, okay? So a lot of people misunderstand AI. And even worse, now we see some really funny things. This is an actual appliance. It's a rice cooker, which apparently needs artificial intelligence to cook rice, which of course doesn't make any sense at all, right? So there is a deep misunderstanding of artificial intelligence, deep learning, machine learning, and what it really is in our society. So in this presentation, I'm hoping to bring an introduction to deep learning, all right? But I want to manage expectations. First of all, we only have 60 minutes. Most of the introduction to deep learning that you can find online go between 3 hours and 5 hours, I would say. So we are going to define terms, we are going to remove some fields, we are going to do a little bit mathematical reminders, and that's what we do. So it's the intent here is to give you basically a boost in confidence and encourage you to continue your self-learning later, all right? I have 62 slides, so it's going to go at a certain pace, I would say. Fasten your seatbelts. It's not crazy. I have a good story, I think, but you know, try to pay attention and we'll go at the rhythm, okay? And finally, I'm not a data scientist, so you may wonder, what am I doing here, talking to you? Okay, I'm not an expert in deep learning. Well, it's very simple. I'm a developer. How many developers in the room? Majority, I think. How many people would qualify themselves as data scientists? Well, nobody, right? Because they don't need to be here. They know this stuff already. And IT pro, maybe, like, you know, network administrator. No, so it's really developers, which is great because this is exactly the audience that I developed the session for. I'm a developer. I speak your language. I was in your seat a year ago, 2 years ago, all right? I didn't quite know those concepts. And then I went through a journey of learning, and I'm trying to bring that to you now. So that's the intent of this session, okay? Good, so let's define a few terms. What is deep learning? What is machine learning? What is intelligence to start with, all right? Intelligence is when you acquire skills, okay, through experience, and then you manage to reuse those skills to survive as cavemen, we did that, or to improve your life, okay? That's intelligence. And so humans have intelligence, at least most have. I have names. I won't name anybody, but most humans, right? Animals have intelligence, okay? An animal is learning new skills to survive, to improve his life, okay? And then we have artificial intelligence, and artificial intelligence is the process of developing algorithms to enable a machine to have intelligence, according to the definition that I gave before. And then we have a subset of artificial intelligence, which is machine learning. And machine learning is basically about teaching a machine to learn from data with minimal interaction. So we don't develop code, we don't give a set of rules to the machine, all right? And then we have deep learning, which is a subset of that, which is a little bit like machine learning, except that we really minimize the human interaction even more, okay? We can teach the machine, but after that, the machine is pretty much learning on its own, according to some algorithms. And that's the focus of what we have here. Good, so there are big differences between machine learning and classic programming. So we know classic programming, all right? In classic programming, what you do is that you take an algorithm, and algorithms are what you go on Wikipedia to look for or on Stack Overflow, okay? We have names. I don't know the names by heart because you don't need to know that by heart. But there are names like lagged Fibonacci generator, topological sort, Euclidean minimum spanning tree. I don't even know what that one does, but complicated names. So you take the algorithm, and then you translate that into code, and then you feed the system with some data, which typically is a small amount of data, relatively speaking, okay? And then at the end, you get answers. And those answers, this is a very repeatable process, okay? If you take the same data, the same algorithm, you will get the same answers, which is why we can do unit tests, okay? In unit tests, we give a set of known answers to an algorithm, and then we get some answers that we can assert, all right? So that's classic programming. Now in machine learning, we are switching things around a little bit, and what we are going to do, we are going to take some answers. Like for example, I'm going to take a picture, and I'm going to tag the picture, and I'm going to tell the machine, this is a banana, okay? That's an answer. And then we take some data, and typically we take some big amounts of data. So in the case of picture recognition software, every pixel is transmitted to the machine, so that's a lot of data, and then we are going to also submit a lot of pictures, okay? In the demos that we are going to see a little bit later, we are taking something like 900 pictures to teach the machine to do image classification, okay? So it's a lot of data. And then we feed that through some frameworks, for example, TensorFlow, PyTorch, these kind of frameworks, CoreML on iOS, etc. And then at the exit, we get an algorithm, which in machine learning, in deep learning, we call a model, okay? And then after that, the process is to use that model with the help of some code and feed some new data into that. And this new data is the production data, the data that you want to test, okay? And then at the exit, you get some predictions. And notice I'm not saying answers here, I'm saying predictions. It's a difference, okay? Prediction is something like, I see your picture and I think it's a banana. I'm about 85% sure that it's a banana, okay? And also the amount of data that we feed the system in order to teach those models, to train those models, is a huge amount of data. And small variations in the data can have some big impact on the predictions, okay? Also, it's very possible that the model keeps learning. So what I'm saying here is that if you submit the same picture twice to a model, it's very possible that you'll get some different predictions at the end, okay? So something to keep in mind. So we may ask ourselves, why is artificial intelligence suddenly such a big topic, okay? Those algorithms that we are using, those models, are very old. All right, the first neuron was developed theoretically, obviously, in a lab, okay, by researchers in 1943. So that's a long time ago. 1955, the first artificial intelligence conference took place. That's 14 years before men went to the moon with primitive computers, okay? So it's a long time ago. But now suddenly, we have the amount of data that we need to train the models. Acquiring the data is not a problem anymore. We have sensors everywhere, okay? We have the possibility to store the data. On Azure, we routinely speak about, terabytes, petabytes of data, okay? I remember 1 year ago when I heard petabyte for the first time, I thought, wow, that's a weird term. And now it feels so natural, okay? So we have that. We have also the possibility to store it, but also to transmit it over the wire, over internet, at acceptable speeds, okay? And then we have the speed of processors, which has improved, and especially GPUs, graphical processing unit. We'll understand later why those are critical for deep learning, okay? So now we have powerful machines, and we also have advances in software. We have new programming languages which enable us to do these, to process those algorithms faster and more efficiently with less code, okay? So all this makes that now the promise of artificial intelligence deep learning is possible after all those years, okay? Good, so let's go to the basics and let's talk about a neuron. So to do that, I'm going to do a little bit, from time to time, some mathematical reminders. So when you see the symbol on the top right, the square root of x, okay, it's just a symbol. It means let's do a little bit math, all right? Because I don't know for you, but for me, I know that this math, I learned that in engineering school, that was 25 years ago, and then I never used that math anymore, okay? And then suddenly I'm like, oh, wow, okay, I need to remember a little bit. So let's start simple. Let's imagine that we have a system with a number of inputs. And those inputs are labeled x1, x2, x3, xn, because we don't know how many inputs we have n inputs, okay? And then let's imagine, for some reason, we decide to multiply x1 by w1, which is a number. And then we decide to multiply x2 by w2, x3 by w3, xn by wn, and then we do a sum, okay? This is a sum of products. And then we send that to the output. And so if we want to write a mathematical formula, because like this we feel very clever at 9 a.m. in the morning, all right? This is sigma. It's a big Greek letter. It means the sum of. And for us developers, we understand that very well because it's like a loop. It's like a for loop, okay? We do for I equals 1 to n, and then we loop, okay? And then we do x1 times w1, x2 times w2, plus x3 times w3, etc. Okay? So first mathematical formula, you're doing great, right? Cool. So now let's imagine that first of all, we are defining that those W's, we are going to name them weights. Why weight? It's because if we take W1 and we set it to 0, for example, then suddenly X1 doesn't have any weight. It's ignored. If we take X2 and we say, okay, we want to give a big importance to X2, you can take W2 and give it a big number, and then suddenly X2 has a big importance. It has a big weight. All right? Cool. And so far, we don't talk about those weights. We don't know how we find them, all right? They are just here at the moment. Now, one thing that we want to do, because the exit, the output, is going to vary tremendously. Maybe it's a very, very large number. Maybe it's a very small number. It's a little bit, it's not very convenient, right? So we want to put a function in the middle, and this function is going to transform the result into something, for example, between 0 and 1. Or between -1 and 1, or between 0 and 10, it depends. It's a little bit depending on the problem that you have. Now, those functions are called squishing functions. I'm kidding, they are not. That's what I call them, because they squish the result. I try to submit that to data scientists. They say, no, we call that activation functions, because they like complicated words. I prefer squishing, personally. So we have activation functions, and so that is the output now. So if we take the formulas that we had before, now what we have is basically a nonlinear function, which is squishing everything, all right? Good. So now there is still one step. Sometimes we want to move the result in one direction or the other. And when we have one neuron only, it doesn't quite make sense, but when we have a number of neurons, like we'll have later, maybe sometimes you want to give a little bit more importance to some of the neurons compared to others. And so we can add a number that we call the bias, okay? Because we are biasing, we are moving the result in one direction or another. It's like an additional knob, you know, like the one that goes to 11. You know, you can turn it a little bit more, a little bit less, like that. Now, this is a model of a neuron. And because data scientists, like every other geek out there, like us software developers, love to use words that nobody else understands, sometimes they call that a perceptron. Okay? Don't ask me why. Sometimes we hear that. But basically, it's a neuron. Okay? So that's pretty good, which means that in the formula, if we add the bias, that's what we have. And here is the formula of a neuron. Okay? By the way, you'll get all the slides at the end, right? So if you want to spare yourself taking pictures, I'll give you all the slides at the end. Good. So, good work. And now let's move to something else, another mathematical reminder, linear algebra. Okay, why suddenly, oh my God, linear algebra? It's very scary. Well, it's not that bad. First of all, let's remind you of what it is, right? So this is a vector, and that's a vector with 2 dimensions. It has an x and a y. 2 dimension is pretty good for my limited brain. I can easily put it on paper, and then I have an angle and a direction, and I know what it is, okay? Good. But now, of course, we can have also more dimensions. We can have 3 dimensions. Now, my limited brain can still process that. I have a vector coming out of the screen pointing at me. That's fine, all right? But then suddenly, maybe I have 4 dimensions, or maybe I have n dimensions, and my brain explodes. But the good news is that computers are great with this type of things, because for them, n dimension is the same as 2 dimension, except that it's going to take more time to process. But they don't care about dimensions. They are not limited by our representation of the world, okay? So why is that important? It's because some operations, like for example the dot product, computers can process that faster. Like for example, a dot product, the mathematical definition is you say, okay, I take the first line plus the second line, all right? So if I generalize that with x1 and w1, x2 and w2, that's what we have, which is very much what we had before with the sum of products, remember? Okay? So if I generalize that with n, I can write this equivalency, which means that our sigma that we had before is the same than the sum, than the dot product of two vectors. But the big advantage is that the expression with the sigma is processed serially, so it's very slow, while the expression with the vectors, computers can process that in just one operation, especially graphical processing unit, GPUs, because graphical processing units have been developed to drive monitors, display. And in monitors, in display, we are using bytes to represent colors, okay? So when they need to do some effects, basically it's a multiplication of arrays of bytes. So they were developed to process that very fast. And now we are kind of misusing, if you want, GPUs, not to do graphical operations. The G is kind of misleading, but because we want to process those arrays of vectors, those arrays of values very fast. Make sense so far? Excellent. Good, so if we take the representation now, it means that we will have something like that. Oops. Okay, this is a formula that we will have, where I replace the sigma by some vectors. Good. Okay, so now let's talk about neural networks. So this is one neuron, and as you see, there is a lot of information on this picture. We have W's, we still don't know how to find them, okay? We'll talk about that later. We have the B, the bias, okay? We have this activation function, which is, basically it's a lot of drawing. So I can simplify the picture a little bit. We are just going to assume that the weights, the bias, and the nonlinear function are still there. I just removed them, but they are still there, okay? So now I could do something like that. That's the same picture as before. And let's say that I want to have two outputs now. So I could do something like that. I have two neurons now. I have double the number of W's and double the number of B's. Okay? Then we could do something like that, where we add here some W's and some B's, and then we add some W's and some B's for a number of times, which is called m here, so we don't know how many times, okay? And this blue line in the middle, this is called the hidden layer. Why is it hidden? Well, it's simply because you can observe the inputs, you can observe the outputs, but the one in the middle, it's a little bit like a black box. We don't really observe it. So it is hidden. That's just a name, okay? So we have a lot of arrows on the screen now. It's a little bit messy. Let's simplify that. It's the same, but except with a different notation. And researchers, because in deep learning, a lot of the learning that we do is by trial and error, okay? So researchers found out that if you add more layers, then the error at the end, your result is more accurate. The error is smaller, okay? So we can do something like that. We can add layers. And to give you an idea, in the demo that I'm going to show you later, I'm going to use a model called ResNet 18, which means that it has 18 layers. If you go to Azure and we have cognitive services, we have one which is doing custom vision, so recognition of objects or classification of images. This is a ResNet 50, so it has 50 layers, okay? That's a lot of W's and B's, all right? A lot of parameters that you can change, that you can influence. Just to give you an idea, so this is what we call a deep neural network, okay? Cool, we are progressing great, right? It's not that scary. Excellent. Let's talk a little bit about the activation function. So that's the squishing function. I propose we all lobby for a new name because activation function, why? Anyway, so there are different activation functions you can use, and it depends a little bit, and again, a lot of this is trial and error. Trying an activation function, and then maybe it gives you some results, and you try another one, the result is better, and so you're rather going to use that one, okay? So for example, one possible activation function is called a sigmoid function, all right? I did some graph in Excel, which is a great plotting tool for this kind of things. So this is how it looks like. And as you notice, the output is going to be between 0 and 1. So that's the main usage of this function, is to transform a big number between 0 and 1. Okay? So that's one possible activation function. Now these days, since 2001 more or less, we are using a lot another activation function called rectified linear unit, or ReLU. ReLU is a word that you will see a lot when you do deep learning, when you check models, when you open models. It looks like that. It's also called half ramp sometimes because it has half of a ramp. And this is the formula for that. So basically we ignore the negative number, we take only the positive ones. Okay? Now this angle at the bottom there, computers don't like that so much because they are difficult to modelize. So sometimes we take an approximation of that which has kind of a curve, all right? But basically we call that a ReLU, a rectified linear unit, okay? Good, so now let's talk about an example. So for example, I'm going to take here 9 squares, those are gray squares, and what is asked from me is to find out if the top row is darker than the bottom row. Okay, it's a simple question, which is actually used in practice when you do, for example, handwriting recognition. Okay, so we want to know where are the dark pixels. Good. Now, in the problem, we ignore the middle row. We don't care about the middle row at all. Good, so I need some inputs. We are going to codify those levels of gray between 0, which we are going to say 0 is white, and then 255, which is black. And I know in computers it's the opposite. Okay, in computers, 255 is usually white and 0 is black. But I'm just going to reverse that because it makes my problem easier, and it's a simple mathematical operation to reverse. Okay, very easy. So for example, here I have 182, it's a medium gray. I have a darker one at 199. I have a lighter one at 90. Okay. You see I have here something which is almost black at 247. I have something down there which is almost white at 4. Okay. So how can we process that? So let's imagine that we have multiple squares. So this is one with the corresponding data. I have another one with the corresponding data. I have 40 of those with the corresponding data. All right. So I want to find a way to automate that. And so let's take an ID. Let's run that through a neuron. So I'm going to have 9 inputs. I have 9 levels of gray that I want to test. Okay? And then I'm going to multiply those by 9 different weights. Then I'm going to do the sum, just like we learned. And then I'm going to run that through an activation function because ideally I would like to have a result between, well, not between, equals to 1. So positive sign if the top is darker, and negative sign if the bottom is darker. So I'm just having a function to transform the result. I'm just going to take the sign of the result. Good, now the first thing, if we take a concrete example, first thing we can do is input those values, okay? And then after that, the first thing I told you before is that we are going to ignore the middle row because we don't care about the middle row. So I'm going to set those weights to 0. I'm just not considering the medium row at all, okay? And then what we can do, we can say, okay, I'm going to take the average of the top, the average of the bottom, and compare which one is the largest. But the good news is because we have 3 values on top and 3 at the bottom, we don't need to divide by 3. Okay, if I divide by 3 on top and at the bottom, it's useless. I can just take the sum, all right? So on top, I'm going to take the sum. I'm going to multiply by 1. Like this, I have a positive sign. And because I want to compare, what I'm going to do is, the bottom I'm going to multiply by -1. Like this, if I have a positive result, like for example in that case, the top amounts to 495, the bottom amounts to -259, so in absolute value, we see that the top is larger than the bottom, which means that the top is darker than the bottom. Make sense? Okay. Which is proven here. It's a positive sign. If I run it through my activation function, I have +1, which means the top is larger. Good. So now what we did here is basically find out the W's, and because I have only one neuron, I don't have a B because I don't need the additional button. Okay, I don't need to move the result. I found the W's by reasoning. Now, computers cannot do that. Computers cannot reason, but they can do one thing very fast, much faster than us. They can try values and see which ones are better than others. They are going to try a large number of values and see how, okay? So before we go into that exactly, and I'm going to show you how it works, let's define a few terms. When you do deep learning, when you learn that, you're going to see those terms all the time: supervised, unsupervised, and reinforcement learning. Supervised learning is what we are doing now. It's basically teaching the computer with some examples, with some answers, and the computer is learning from that, and then creating the model, okay? That's probably the most common one. This is great for things like classification, which means you submit an image and it's going to tell you it's an apple, it's a banana, it's an orange. Now there is also unsupervised learning, which is basically the computer is going to go through the data and it's going to find clusters, to find some groupings that it can do. And it's going to do that automatically without human interaction, okay? Now this one is great to do, for example, object detection, because the computer is going to check all the pixels and then it's going to find the edges of the pixel, which is basically clusters of darker pixels, for example. And then it's going to translate that into, oh, that looks like an eye, that looks like a cup, that looks like, you know, something, etc. So then it's going to be able to tell you, I see the face of a person and draw a square around it, okay? So unsupervised learning is newer, and we're not going to talk more about that in this session. We are going to concentrate on supervised, but if you're interested, you can also check it out. The other thing is reinforcement learning. That's a little bit like training a circus animal by rewarding the good behavior, okay? So you'll see those three terms quite often. Here we are going to concentrate on supervised learning for the moment, which is quite common for classification. Good. So let's do another mathematical reminder, because I would like you to remember how to calculate the slope of a function. That's going to be important later, okay? So if we take a function, this is square of x, okay? And let's say that I want to run a straight line through 2 points. The slope of the straight line is defined as the vertical distance divided by the horizontal distance. That's what it is. So basically delta y divided by delta x. Now I have the slope of the blue line, but if I want to have the slope of the blue line when it is just in one specific point, which is basically the slope of the orange function, what I need to do is that I need to make x smaller and smaller and smaller, okay? So in math, we say we are letting x tend to 0. We are making it smaller and smaller and smaller until x and the other point are just 1 point. And so we are going to have a very small y, but then we can basically calculate the slope, okay? Now this is something that we learn to do, for example, in engineer school or maybe in computer science school in math class, all right? We learn how to calculate those functions. For example, the derivative of x squared is equals to 2x, okay? It takes a lot of time. First of all, we need to remember how to do that, and I'm going to be totally honest with you, I don't remember how to do that, okay? Good news, you don't need to, because computers are great at doing these kind of things, okay? Much faster than we can anyway. So now we know how to calculate the slope. We are going to use that in a moment. So how do we find out those W's and those B's? Well, remember, we are feeding the computer some answers. So the computer knows what the result is expected from it. Okay, we are going to say, I give you a picture of a banana and I tell you it's a banana, and you better find out that it's actually a banana. Okay, good. So what the computer is going to do is going to try different values of W's and B's until the error is as small as possible. And this is called error reduction, but because data scientists love complicated words, we call that actually loss reduction. Okay? So loss reductions works like that. Imagine that you have a system with two inputs. So we have two W's. And imagine that we have the possibility to plot for every value of W1 and W2 the error. Okay? Don't forget, we have the answers. We know that. Okay? So that could look like that. Suddenly we have a 3D graph with just two values. Okay? So, of course, plotting all the values, all the points for every W's, remember we can have thousands, maybe millions of W's in a complex system, right? That's going to take way longer, maybe too much time, even for a fast computer. So instead, we are going to try things like that. We are going to say, what we want to do is try to find the lowest possible error, the value of W1 and W2 for the lowest possible error, okay? So what the computer is going to do, it's going to choose a random point. And then it's going to calculate the slope. Remember the derivative function, right? It's going to do that, except it's going to do that in n dimensions, because maybe we have n number of w's, okay? So it's going to calculate the slope, and then it does that until it finds the steepest slope. And then it's going to take a step in the other direction. It's going to take a step down, a step reducing the error, okay? Now, the value of these steps, the length of these steps, depends on the system that you are using. If you have a system that you know well, you can take a big step because you know pretty much what's going to happen. You're not expecting a lot of holes on your way, okay? If you have a system that you don't know well, you take a smaller step, and this step is called the rate of learning, all right? So now we take steps until, hopefully, we end up in the deepest possible hole, which is the lowest error. But of course, sometimes it doesn't quite work this way. Sometimes maybe we are going to end up taking a wrong turn, and then we end up in a hole, but it's not the deepest hole. This is a local minimum. It's not the global minimum. So to avoid that, what we are going to do, we are going to try a number of times, and every time we are going to start with a different random point. Okay? And those iterations, those trials, are called epochs. And those are necessary because this is an actual representation of a loss landscape. And as you can see, there are a lot of local minimums. There are a lot of possibilities for the computer to take a wrong turn and to end up in a minimum, but not in the minimum. Okay? So that's why we have those epochs, those iterations. Okay? And for example, in the demo that I'm going to show you, we are going to try 25 times, which of course takes a long time. Okay? Good, so in practice, this technique is called gradient descent, okay? We are going to find the steepest gradient and then we are going to descend. Now that's taking a long time, as you can imagine, because every time we have to calculate the derivative to have the slope and then take a step and then calculate the derivative in different directions until we find the steepest slope, take a step. It's taking a long time. In practice, we use something called stochastic descent. Again, very complicated word. Actually, it just means random. They are just going to try random directions until they find a value which is reasonably low for the error, which corresponds to a good number, a good set of W's and B's. Okay? Good. So let's do a demo. And for this demo, I'm going to use somebody else's knowledge, my colleague Cesc Juarez. He's an awesome data scientist. He knows this stuff much better than I do. Okay? And he agreed, he helped me, first of all, to prepare that session, and he agreed to let me use the demo. So we are going to see how a real data scientist is doing this kind of things. All right? So thank you, Cesc, so much. We are going to use different tools. The first tool we are going to use is Python, the programming language. And why are we using Python? It's because it's a good language, good programming language to do mathematical operations. For example, the dot product of two vectors, that's built in the language. You don't need to program it yourself, it's just built in. A good contender could be R, the letter R. Okay? This is also a programming language which is used a lot for statistics. But it seems these days that the community of data scientists is rather using Python to do machine learning and deep learning. So that's why we are going to use it here. Then we are going to use one of those frameworks to train the model. Okay, so I told you that one possibility is TensorFlow. It's a well-known framework. PyTorch is very popular these days as well. It's a little bit newer, and so says here is going to use PyTorch to train the model. And those frameworks, PyTorch, have things built in, such as activation functions, or even a whole model, the ResNet 18 that I mentioned before, the model with 18 layers, okay, is just built into PyTorch, so you can just take it and train it. So that's convenient. Then Cesc is going to use Jupyter Notebooks. So Jupyter Notebooks are a tool that runs into a web browser. It's using Python, which is installed on your machine to process the calculations. And this is a cool tool if you want to try things out. So usually, data scientists publish their algorithms as Jupyter Notebooks. you can download it, okay? It's basically a text file with a series of instructions and some Python code. And then you open it in Jupyter Notebooks in your web browser, and then you can run step by step. And for every step, the data scientist can write some instructions and tell you what to do. So that's a great way to learn, okay? Another good feature of Jupyter Notebooks is that they have a very nice integration with Azure Machine Learning, Azure ML. And so from Jupyter Notebooks, you can actually interact with Azure ML, like we will see in the demo. So it's really convenient. We are going to use Visual Studio Code to do a little bit of edition of Python code. It's not totally necessary. You can use basically any text editor, but Visual Studio Code has some Python extensions, so it's quite convenient. For example, if you want to do syntax checking, this kind of things, all right? And then we are going to use Azure Machine Learning because, as you will see, once the code is written, we are going to try once on our machine, on a local machine. We're going to do one epoch, one iteration, just to check that everything goes well, and that's going to take a long time. So if you want to try 25 epochs, it's going to take even longer. So we need a powerful machine to do that, and we are going to just delegate that work to Azure, because on Azure we have very, very powerful data science machines with a lot of very powerful GPUs, and so you can use them for a while, okay? And finally, once we have our model trained with those 25 iterations, we are going to publish the model as a container, because it's easier, in Azure Container Instances. Another alternative could be Kubernetes or any other registry. Azure Container Instances is probably the easiest way to publish quickly a container and use it. So that's why we use it a lot in this constellation, okay? So then at the end, we are going to end up with a URL with the address of a service, which is the models that we trained. Good, so let's see this demo. So the demo was recorded as a video, and I'm going to play it, and I'm going to pause and explain to you what's happening, okay? So first of all, Seth is going to start Jupyter Notebooks, opens in the web browser, like I told you. Then he's going to open one of the notebooks. And as you can see, what he did is what most of us do when we write code. He went online, found an example, and then changed it. Okay, that's how we do programming. Let's be clear. Okay, so that's cool because there are tons of examples online that do image classification, and that's what we want to do here. We want to recognize pizzas from hot dogs, which is, I think you all agree, a very critical task for humanity. So we are going to use PyTorch. As you see, he's importing PyTorch. And then after that, we are going to start by transforming the images, because we have all kinds of images, all kinds of sizes. We want to normalize them, so we are going to crop them, to cut them, to transform them until they all have the same size. And then we are going to do a little bit of representation here. And then we are going to train the model. Now notice here, this is the number of epochs. By default, it's set to 25. But here, the first time that we are going to run this code, we are just going to try one epoch because we just want to check that it's running correctly. Then we want to refine the model. We want to train the model better on Azure with 25 epochs, 25 iterations. Good, then after that, we go down. So here, this is where the training is actually taking place. And you see we have a training loss. Remember the loss, the error, okay? So here we see two values. We see the loss, which is here at 70%, which is quite large, okay? And then we see the accuracy, which is kind of the opposite. The accuracy is how good the model is, which is at 71%. So on the training, it didn't do great, okay? But then we have another path that we did, which is a validation. And why do we have training and validation? I'll explain that to you a little bit later. Validation is just saying, I'm going to try the same model with a smaller set of images and check the results, just to double check. And we'll see later why that is important. Here, you see that the training took 24 seconds to complete. It's just for one iteration, okay? It's not too bad, but still, the set of images that we have here is not very big. And then after that, we are going to show the result directly in the notebook. And then we are going to save the model locally so that we can reuse it later. Okay? So here, Seth took that Python code, put it in Visual Studio Code, changed a few things so that he can run it locally. And that's pretty much the same thing than running it in the Jupyter Notebook, but it's just to show you that you can also run that locally. So you do Python train with one epoch, okay, one iteration. And so it's going to take a while. Now I'm speeding things up in the video quite a bit because I didn't want to let you just wait. And we're going to see, this is a gradient descent which is happening, okay? It's checking the loss until it gets a value which is low enough. And the results here are very similar to what we had before. The model is saved here locally. We have two formats for the same model. One is saved as an ONNX format. ONNX is just a standard format for saving artificial intelligence model. And that is what is used, for example, by Windows ML. Okay? So if you do ML.NET and you want to program, ONNX is good. There are other format for the same model. For example, here we have the PyTorch format for this model, but basically that's the same model, just is saved twice. Good. And by the way, you can open those models. There is a tool called Neuron that you can use. And you see what we have here. Those are the layers that we have. We have different layers with some W's and some B's. Here we have some W's, here we have some B's. Here we have a ReLU. Okay, we know what a ReLU is now. It's a rectified linear unit. This is an activation function. And as you can see, we have a number of those layers. Okay, I told you he was using an 18-layer deep format, and at all times you can go and observe the values that were found by the model. So now we have another Jupyter Notebook, and I told you that you have an integration between Jupyter Notebooks and Azure Machine Learning. So this is exactly what it's going to do. It's going to take exactly the same model, but this time it's going to train it in Azure because we don't want to wait that long. So here, this is going to create a compute environment, or rather to take a compute environment. Okay, we have a batch of them available in Azure ML. We take one, and then the data for those models is going to be, the training and the validation data are saved in Azure in a blob storage. So here we see these values, and for example, we have what appears to be a very delicious hot dog, very American hot dog, I should say. And then we are going to run the experiment. Now that's going to take a long time. So again, in the video, I speed things up tremendously, all right? So here, this is starting up, all right? You see here the time is speeding very fast. We're already at 2 minutes. All right, this was pretty much just waiting. Then we start seeing things happening. You see the epochs are happening, and as the epochs are processing, we see the curve. So we see the accuracy, which tends to 95%. We see the loss, which tends to 0. You don't really want to have a loss of 0. I'm going to tell you later why. And then at all times, you can always see your results on Azure as well. So here we have an Azure Machine Learning workspace where you see the same graphs. Everything is saved on Azure. The models are here, and we have logs, etc. So then the models have been saved. Then we can create a container image, all right, that we are going to deploy to Azure container instances directly, which means that at the end, after this is finished, everything takes longer, right? But I'm speeding things up in the video. At the end, we are going to get a URL, and that's going to be the URL of our service. So let's go online and find some beautiful pictures of pizzas. All right, that's a pizza. So here we are going to start. This is a program a little bit like Postman, okay? It's just something to post some requests over HTTP. So here we have the address of the container that we had just before. We are going to copy-paste the URL of the pizza, and we see that the result is correct. It's a pizza. Good. Then we are going to do the same thing for a hot dog. All right. Copy the image, and as you would expect, the model says it's a hot dog. Success. All right. So that's basically how data scientists train those models that we as developers are using. Make sense? Cool. Awesome. Good. So now come a part which is a little bit more difficult. There are some issues that we need to solve. First of all, there is a technical issue, but then there are also some non-technical issues when it comes to AI, and I really wanted to reserve 10 minutes of this talk to talk about ethics, ethical handling of AI, the problem of bias, which is not the same bias as before. We'll define all that. So first of all, the technical issue Overfitting. So there are a few things that I showed you, and I said I will tell you about that later. First of all, I told you, we have training pictures and validation pictures. And then I told you, you don't want the loss to go to 0. Okay, why? Well, you see, the problem is that we want to generalize our model. Okay, so we're going to train the model with a set of pictures, but then after that, we want to generalize to other pictures. So if you have a cluster of points like that, and you try to run a straight line through it, very fast you will notice that you can't really stick to every point. It's not perfect. So in data science, they say that this is underfit. The model is underfit. And then maybe we try a curve, and then we see, oh, that's pretty fit. Fit means it's not perfect, but it's good enough. Okay? But if you give that to a computer, the computer is a perfectionist. He's going to try a curve like that. Okay? That's a mathematical function that the computer invented, and the loss, the error is 0. It goes through every point. So it means that on the training data, your error is going to be 0. But then when you try to different data with your actual data, then suddenly the error is going to be too large because it's sticking to the training, but it's not generalizing well to other data. Does that make sense? You understand the concept here. So here we say the model is overfit. Okay? Overfitting is not good. You don't want that. So there are two ways to solve that. The first way is to do what we all do on a Friday night. You kill 50% of your neurons randomly. Now, computers are really cool because they can regenerate those neurons much faster than we do. So basically, we say on every epoch, on every iteration, we are going to make the model just a little bit dumber by killing some of the neurons randomly. And then the next iteration, we are going to kill another set of neurons. That's one way to solve overfitting, by making the model a little bit dumber than it really is. Okay? But probably the best way is to do that, is to try with some validation data. And so what it means is that you're going to say, all right, if I have a number of iterations and my loss during the training wants to tend to 0 as I increase the number of iterations, but then you try with the validation data, which is a different set of data, then you're going to notice that at some point it's going to diverge. And it's exactly at this point that you want to stop the iteration. So you don't want to train your model too well, because if you train your model too well, it's not going to generalize well. Okay? Good. So that's overfitting. So that's good, but then there are other issues that we unfortunately cannot solve that easily, and those are ethical and moral issues. Okay? So some of the issues are just the normal issues that you would see every time that there is a new technology arriving. All right? AI can be used to improve, in quotes, weapon system. All right? Theoretically speaking, you could leave a kill, no-kill decision to an automated weapon. Now, in our Western countries, we don't do that, but we know that there are some other countries which maybe are not that reluctant to do these kind of things. That's a danger, of course. But I would say that's what happens every time you have a new tech. All right? It can be used to spy on people, of course, for example, with face recognition, all right, with classification, with detection of suspect behavior. But who are you to decide what is suspect? All right? I like to do things that in other cultures might be unacceptable, like, I don't know, eating pork, for example. So if suddenly somebody decides that it's suspect, then I have a problem, okay? Privacy, we are working with big amounts of data, all right? This data may not leak. You may not use data to train a facial recognition software without asking the person first. Even if the data is anonymized, it doesn't matter, okay? That's a moral issue, that's a privacy issue. You should not do that. Then there is the issue of deepfakes, because those models are so powerful these days, they can actually create videos where they replace the face of a person, they take the face of a person and they put it on the body of another person in such a seamless way that it's almost impossible to notice the difference. If you go on YouTube and look for deepfakes, first of all, be careful, because some of that is really not suitable for work. Okay, there is a whole dark portion of YouTube dedicated to deepfake. But there are also some amazing things where, for example, they take a picture. Recently, there was something like that done with a picture of Salvador Dali, for example, and then they animate it in a video, which is absolutely amazing, right? So that's the bright side of deepfake. And then right in the middle, for some reason, apparently they do a whole lot of deepfakes with, what's the name of the actor in The Rock? Nicolas Cage, thank you so much. For some reason, I don't know why, they do a whole lot of deepfakes with Nicolas Cage, where basically Nicolas Cage is playing in every possible movie, The Matrix and everything, the Godfather, right? So I would say that's kind of in the middle between good and bad, right? It's like, well, maybe more direction bad. So deepfakes, check it out. Be careful when you check it out. Don't have kids around, right? But it's quite fascinating, really. There is a video that, if you're interested, you can come to me and I'll show it to you, where they put a fake mouse on Obama's face and they make Obama say things that he never said, which is crazy good, in the sense crazy well done. But of course, it can be also crazy dangerous, right? Good, so those are some of the ethical issues, but then there is another thing which is really a big problem, which is the issue of bias. And that's not the same bias as the B in our neuron, okay? It's bias in the sense, it's like when you have an inclination towards something, all right? And usually bias is considered as a negative thing. So what is bias really? Well, you see, the problem is that our AI models essentially are math. And there was a big debate a few weeks ago in the US between somebody from the left and somebody from the right, I'm not going to name names, where basically the one on the left said, oh, AI is biased, we need to be careful. And the one on the right said, no, you are so stupid, because apparently that's how we do politics these days. No, you are so stupid, AI is just math. Math cannot be biased. And of course, it's true, math cannot be biased. 2 + 2 = 4. That's true on Earth, on the Moon, on Mars, in our known universe. I didn't go and check in other universe, but in our universe, 2 + 2 = 4. There is no bias. What can be biased, however, is the data that we get, the data that we collect, okay? So let me illustrate that with an example. A few years ago, some researchers decided to do an AI model that was going to take patient history and based on that detect or predict if a patient was more or less susceptible to get pneumonia. Now that sounds like a great idea because it's going to assist doctors, all right, that's really cool. But then they found something really weird. They found that consistently the model was predicting that an asthma patient was less at risk to get pneumonia. Now if you think of it from a human standpoint, it doesn't quite make sense because somebody with already an affection of his respiratory system, you would think he's more at risk to get another affection of the respiratory system. So what was actually happening is that the patient was actually listening to his body a lot more than other non-asthma patients did. And then they were detecting, oh, something is not quite right. They would go to the doctor early. The doctor was checking them and was treating them early before they were actually getting pneumonia. Okay? So it was something completely different. So now you see the danger because, of course, it means that if you submit an asthma patient to the system, it's going to say, oh, you're fine. You have asthma, that's cool. You will never get pneumonia, which is, of course, wrong, okay? So now, in that case, they code it, which means that they can fix it in the data. They can, change the model, but it's very dangerous because if you start changing your data set, your model, you don't know exactly what can happen, and most importantly, you don't know what else you missed. Maybe there were other factors that they didn't notice, okay? So then at the end, they decided to really question the whole model. They decided to actually discard the experiment. This system is not used, okay? So bias can be very dangerous because our society is biased. This bias is translated in data that we collect. And for example, there is racial bias. Now this is a quote from an article. I'm sorry for the black word, okay, but this is really a quote from the article. I didn't want to show pictures because those pictures are very offensive, in my opinion, where basically Google Photos tagged automatically some people of colors as gorillas, which is, of course, horrible, okay? I don't understand how it's possible. I don't understand why a human didn't code that before a user actually coded it, okay? And what happens here is that the system was undertrained with people of colors. So the whole data set that they were using to train the system was biased, and unfortunately with the same bias that we have in our societies. Racial bias is a big problem because sometimes some, and Stacy, I'm sure you know that, some law enforcement offices are using facial recognition to predict if somebody is more likely to commit a crime or less likely. And of course, if you have a bias against people of color, then you see the problem, right? And also those systems use algorithms like, for example, okay, if somebody's brother committed a crime, then that person is probably more at risk to commit a crime, which is not really fair. It's not really ethical to do that, okay? So that's one issue. Then we have, of course, gender bias, because again, our society is biased towards gender, and especially the workforce. Now here, every time I'm in the eastern regions of Europe, I'm so happy because I see many more women than when I'm in Western Europe or in the US, okay? We have more of you here, and kudos, continue to do that. But the fact remains that the machine learning workforce, 85% is male, and I would say even white male, most probably, okay? Guilty as charged, right? So we need more emotional intelligence. Those training data sets are biased, definitely. And one illustration of that is that if you show an AI a picture of a kitchen, it's more likely going to associate that with a woman than with a man. With as a hobby cook, I love to cook, I find this deeply offensive, personally. So those are problems that we have. And unfortunately, it's not an easy problem to solve, because the math cannot solve it. You cannot go and debug your model and find the bug and then solve it and everything's fine, right? It's way more complicated than that. There is not just one solution that you can apply to solve that issue. And if you try to say, oh, I don't want to have gender bias, I'm just going to go in my database and remove the gender column from my data set, well, it doesn't work, because the bias is still there. It's just expressed differently. Or even worse, by treating the bias, you actually added a new bias. So if you say, oh, okay, I want to have more people of color, I'm going to go and oversample that population, then you add another bias to your data set. You see what I mean? So this is a big problem to solve. What you need to do, however, if you use AI, is understand that there is bias in our society, okay, and understand that this bias will also be represented in your AI. And AI is great at picking our flaws and our bias and our problems. It's great at doing that. So those systems, those issues will appear. So what can you do? Well, first of all, you have to be fair when you sample your data, for sure. Okay, sample everyone fairly. But also, very important, remain able to understand the model. It means that if your model is super complex and you don't understand what's happening anymore, then you have a big risk. All right? Need to validate your results all the time. Like in the pneumonia example, a doctor said that doesn't make sense. Asthma patients are not immune to pneumonia suddenly, magically. It doesn't make sense. They went to validate the result, okay? Assume that something will go wrong, because it will, and keep watching your system always, all right? So basically what I'm telling you is that the collaboration between humans and AI is the key to using those technologies, all right? There are numbers which show that, for example, in breast cancer detection, if you have a human, a doctor doing the analysis, he gets some results. If you get an AI and you submit the picture to the AI, he gets some results. But if you have a collaboration between those two, the studies show that the error rate can drop by 85%. This is huge, okay? So collaboration is the key. AI is not here to replace humans, it's here to assist humans. Like Tim said yesterday in his keynote, it's a tool that we are using.